Hey everyone, this video is going to give you some feedback on the first assessed quiz for big decisions. Okay, so we're going to cover 6 questions in this presentation, and this is the first one. Before I get started, I want to give you a little bit of advice to help you get the most out of this presentation. That advice is to do as much as you can to answer and understand the questions before you hear my explanation. Doing this helps lay the sort of groundwork that allows you to understand the reasoning. You've got to build some kind of framework in which to fit what I'm telling you. This sort of echoes some advice that one of my lecturers gave me while I was studying psychology, and that is to beware false fluency. Uh, Apparently, people have a tendency to trick themselves into trick themselves into thinking they understand content much better than they actually do. And a prime example of when this happens is when you have a practice exam with the answers to the questions in the back, and you spend a little bit too much time looking at the answers before trying to understand the questions and answer them yourself. That is a surefire way to fool yourself into thinking you know the content better than you do. And it's actually the reason lecturers can be reluctant to provide answers to their practice exams and tests. Okay, let's get started. With this question, I encourage you to pause the video now, read the question, have a go at it yourself. You might end up getting a different answer to the one you actually gave in the actual quiz, or an answer that's different to your original answer. And if you're looking at this this presentation, it probably means that you got a few questions wrong in the quiz. So if you can get a different answer, that's a good thing. All right, so I'll assume you've read the question and had a go at it. Now let's look at a little visualization of what's going on here. Okay, we have 2 circles here. Each circle represents a different event. And let's say these events exist within a larger universe of possibilities, which is represented by this gray rectangle. And we're also going to say that events must happen within this rectangle. This rectangle is the universe of all possibilities. So there is a 100% chance that an event inside this rectangle will happen. So we're going to call the blue circle event A, and the green circle is going to represent event B. Now, what event? What are we talking about? Well, it doesn't strictly matter to answer the question, but to help illustrate the point, let's imagine we've got a fly that's going to land somewhere within that gray rectangle. It's completely random. We don't know where it's going to land, but it's going to land somewhere. As I said before, the probability of the event being somewhere inside the gray rectangle is 100%, so this fits with the fly landing analogy. 100% chance it's going to land within the gray rectangle. What's the probability that it lands in the blue circle? Well, that's equal to the area of that circle, or I should say more accurately, it's equal to the proportion that area is of the greater area of possibility, which in our example is 0.2. So if the area of the rectangle is 1, the area of the blue circle is 0.2. In other words, the blue circle is 20% of the area of the rectangle. Similar case for the green circle. That's 10% of the area of the rectangle. This translates into probability because the probability of the fly landing in A is 20% or 0.2. The probability of the fly landing in B is 0.1 or 10%. Now, in answering the question, hopefully you notice that the probabilities of A and B add up to 0.3. 0.2 plus 0.1 equals 0.3, right? Okay, now the question I want you to consider is, what is the probability of our fly landing in the blue circle or the green circle? Now, hopefully you can see from this diagram that the probability of landing in A or B is less than 0.3. It has to be because when you add these two areas up, you get 0.3, but the combined area of the two after you take out, well, the combined area of the two is 0.3, but this new shape that's created by overlapping them has a little overlap here, and you can't count if you just add A and B. Well, sorry, if you just add the areas of A and B together, you'd be counting the overlap twice. So for the probability of A or B to equal 0.3, you need to get rid of the overlap. Now, these two events are now disjoint. That is the word that is in one of the options on the previous page. That was one of your choices of answers that you could give to the question. And sorry if you didn't get it, but that's how we learn. And hopefully this little explanation helped. Okay, next question. Again, please pause the video for a moment so you can read it and have a go at it. Okay, so as before, there's a funny little word in there that's not that commonly used, or it's not that commonly known, and that word is empirical. If you don't know what that means, please look it up. And when I say that, what I mean is I hope you looked it up. What an empirical theory is, and you'll have to forgive me if I get this slightly wrong, it's a theory based on observation. The philosophers James Chase and Richard Corey might be able to give you slightly better, more accurate, or even more precise answers than that, but that's my working understanding of it. So in this situation, Barbara has decided that if she's really sure of something, she's going to assign a degree of belief to it of 0%, and then if she's really sure of something, she's going to assign a degree of belief of 100%, and then 0% if she's really certain it's false. So she wants to use extremes. I hope when you look at this this scenario, you think of the Jura game. You think of Barbara's Life on Mars example. A good Bayesian does not work with uncertainty. She does not trap herself by being overly confident or certain in her beliefs, because certain beliefs cannot be updated. And no matter how certain you are of something, you don't know everything, and there is always the possibility that you are wrong. All right. Now, similarly, Bill also wants to assign degrees of belief 0 and 100%. Or, sorry, he wants to assign degrees of belief of 0 or 100%. But he wants to do so for different reasons. He wants them to reflect the importance of the theories. If something's really important, then he wants to assign a degree of belief reflecting a probability of 100%. Now, this isn't how Bayesianism works either. Despite the fact that we shouldn't assign degrees of belief of 0 or 100%, we also need to be aware that a degree of belief shouldn't depend on the consequences of that belief. A reason you might get mixed up here and think that Bill's doing the right thing is because it's kind of similar to what we did with expected value. Now, with expected value, you get the probability of something happening and you multiply it by the value of that thing happening. And then you do that for all the different possible outcomes and you add them together. And I'm going to show you about this on this slide. This is just a quick revision of expected value. You can read through that. Maybe just pause it for a second if you want to read it, but it's worth pointing out, and as many of you notice, expected value or use the expected value method of decision making does not necessarily capture everything, especially when the outcomes are hard to quantify. There's also the problem of diminishing returns of value that come with risk aversion. So if you're risk averse, losing $1,000 is not a tenth as good as winning $10,000. There's a non-linear relationship between gains and losses, and some people would rather keep $1,000 than risk losing it for $10,000. It's not a tenfold gain in value. Or there's something like a billionaire, if they put down $1 million to win another $1 or to win another $100, they can do that, and if they lose, they could probably do it again. But if you do that and you lose, you'd be in big trouble because you probably don't have $1 million. So yeah, that is one of the problems with expected value, the expected value approach. But anyway, I digress. It's not exactly part of the quiz. So as before, I want you to just have a quick read of this. Unpause the video when you're done. Okay, hopefully you had a try at answering the question. The way I approach this question is I read the situation and then I start looking at the possible answers. I get to the first one. Alex should decrease her estimate of the probability that stock market will crash. Okay, why would she do that? I guess she would be using Bayes' theorem.